AB Physics 1, 2019, pre-response question 1. Identical blocks 1 and 2 are placed on a horizontal surface at points A and E respectively, as shown. The surface is frictionless except for the region between points C and D, where the surface is rough. Beginning at time A, block 1 is pushed with a constant horizontal force from point A to point B by a mechanical plunger. Upon reaching point B, block 1 loses contact with the plunger and continues moving to the right along the horizontal surface towards block 2. Block 1 collides with and sticks to block 2 at point E, after which the two-block system continues moving across the surface, eventually passing point F. A. On the axes below, sketch the speed of the center of mass of the two-block system as a function of time, from time A until the block passes point F at time Tf. The times at which block 1 reaches point A through F are indicated on the time axis. So the question is asking us to sketch the speed of the center of mass of the two-block system. So that means we'll be focusing on the speed of block 1 here and block 2 here. So let's go back through the problem to see what information we could use to graph the speed versus time graph. So identical blocks 1 and 2 are placed on a horizontal surface. So even though it doesn't say it's explicitly at rest, we can initially assume that they are since it's just placed on the surface. So then beginning at time A, block 1 is pushed with a constant horizontal force from point A to point B. That means block 1 at point A starts moving, but block 2 still stays at rest. So let's ignore block 2 for now until it starts moving. So back to block 1, it's pushed with a constant horizontal force. So due to Newton's second law, we know force is equal to mass times acceleration. So with the presence of a force, that means an acceleration also exists. And since acceleration, which is the change in velocity over time, that means if there's an acceleration, the velocity is increasing. So we can first start off sloping line from point A to B. If you don't know already, for a speed versus time graph, acceleration would be a linear sloping line. So the next part of the problem says, upon reaching point B, block 1 loses contact with the plunger and continues moving toward the right. So that means at point B, there's no more plunger. In other words, there's no more force. And with no force, then there's no acceleration. That means there's no change in velocity as time passes. In other words, the speed stays constant, so we can draw a flat line from point B to point C. Next up, we have from point C to point D. And earlier in the question, it says that from point C to D, the surface is rough. So over here, you can see that this part is denoted by a rough surface. That means there's friction. And friction, which is shown by this funny looking F, is also a force. So it's also equal to a mass and times an acceleration. However, a characteristic of friction is that it opposes the direction of motion. So since we're moving towards the right, the friction will be acting towards the left. And in the left, that's the negative direction. That means the force is negative, and thus the acceleration has to be negative. So opposite from earlier, we will have to draw a downward sloping line from point C to D. Keep in mind, the line doesn't go to 0 as it's still moving towards the right, meaning it still has some velocity. Now from point D to E, there's no more friction, nor is there the plunger. So like from B to C, there's no force acting on it, so there's no acceleration. That means, like from B to C, we can draw a flat line. The last part of the problem says that at point E, block 1 collides and sticks to block 2. Then the two-block system continues moving across the surface. So after reading this, you might recognize that it's an inelastic collision. And in an inelastic collision, momentum, which is P, is conserved. So initial momentum is equal to final momentum. And since momentum is equal to mass times velocity, that means mv initial is equal to mv final. Since the mass of our system is block 1 and 2 before and after the collision, that means the mass initial is equal to the mass final. But since momentum is conserved, that must mean the initial velocity will equal the final velocity. So in other words, our velocity won't change after and during the collision. So we can continue our line from earlier, as no speed is gained or lost. And that would be part A for the first question. Part B. The plunger is returned to its original position and both blocks are removed. A uniform solid sphere is placed at point A as shown. The sphere is pushed by the plunger from point A to point B with a constant horizontal force that is directed toward the sphere's center of mass. The sphere loses contact with the plunger at point B and continues moving across the horizontal surface toward point E. In which intervals, if any, does the sphere's angular momentum about its center of mass change? Check all that apply. So the question asks, when does the sphere's angular momentum about its center of mass change? So we want to find whenever angular momentum changes. And that only occurs when there's an external torque, which is equal to inertia times angular acceleration, or it's also equal to RF sine theta. So in RF sine theta, F stands for force. R is the distance from the center of mass to the contact point of the force. So let's go and see how this applies. So we have to look whenever there's a force, first of all. And if you remember from earlier in A, the only points of a force is from A to B due to the plunger, or from C to D due to friction. So we can cross out B to C and C to D. So let's look at A to B first. Let's draw the ball, and here's the center of mass. The plunger exerts the force horizontally towards the center of mass. And R is the distance from the center of mass to the contact point. So this distance is R. Now, you're wondering, since there's a force and there's an R, you might wonder if there's a torque. However, there's one more component to the equation, and that is sine theta. As you can see, the force applied and the R value is parallel. That means the theta value is equal to 0. And sine of theta, or sine of 0, is also equal to 0. So that means the torque at the end is equal to 0. So that means there's no torque and angular momentum won't change. So we can cross out A to B. However, from D to E, let's draw another diagram. Here's the ball and the surface. Here's the center of mass. And the contact point of the friction is from here. And if you remember from earlier, friction opposes the direction of motion. As we're moving towards the right, friction will be acting towards the left. So let's use red to draw the friction. And the R value is from the center of mass to the contact point of the force. So this is the R value. So now we have to look at the data here. And since you can see that it's perpendicular, that means theta is equal to 90 degrees. That means at the end, torque is equal to just RF, since sine of 90 degrees is equal to 1. That means a torque exists at D to E. That means angular momentum does change, making this the answer. So we take all this information and write it into a paragraph. So angular momentum only changes when there's an external torque. This only exists in the interval from c to d as the force of friction, and that range contributes to a torque. All the other intervals do not have any torque to change angular momentum.